Hi, welcome to Hard-Boiled Synthesis, Lecture 19, where we continue our synthesis of catnip as a repellent to mosquitoes. In the last lecture, it was very exciting in that we began the analyses. After a bunch of lectures and many hours of work, we could finally start looking more deeply into whether or not catnip is an effective repellent to mosquitoes. And an interesting outcome of just doing like a simple random effects meta-analyses with no predictors or moderators. That's what today's lecture is about, is looking at those things. I'm just doing an average across all the effects that I had. It indicated, to my surprise, that catnip performs just as well as DEET. Okay, so they're on a similar playing field here in terms of repellency against mosquitoes. Today's lecture, though, is to really dig down and evaluate whether or not that was an appropriate test to begin with. In order for me to walk away from this class with high confidence to say that catnip is equal on terms of DEET as a repellent to mosquitoes, I have to do a bunch of stuff. I have to do a bunch of statistical analyses to verify, to double check whether or not that original simple meta-analysis is appropriate for the data. A key assumption of just like taking an average across all the effects, across all those studies, is that they represent a homogeneous group. And that seems like a mouthful, but basically let me describe a scenario here. Okay, so here really we are synthesizing across many species of mosquito, many types of experimentations, right? Different approaches to assess repellency effects. People sticking their arms in cages, people sitting outside with repellents or not repellents. Different ways to use catnip as a repellent. Most of the studies use catnip not straight up as like the plant, but they use essential oils. So you get the essential oils from the plant, and then there's an additional group of studies that go a step further and isolate specific compounds from the essential oils and then test those compounds. Those are a lot of things to just kind of average across of. And so today's purpose is to start using a meta-analysis to break apart the data set to test whether or not there is variation beyond sampling error that could contribute to repellency effects associated with catnip. Maybe it wasn't okay for me to average across all the species of mosquitoes. There's no reason to expect that all the mosquito species would respond similarly to catnip. There's no reason to expect that catnip oil would be just as effective as some of its isolated active compounds, the nipidolactone. And so, even though I walked away from the last lecture with the phrase, "Oh boy, catnip is just as effective as DEET," that's not an adequate conclusion yet, because I still have to verify and assess whether or not it was okay for me to do that analysis in the first place. And so today we're going to throw in a bunch of categorical predictors. These are predictors where I could group into categories. They often have like a hierarchical structure where things that are similar are grouped together, and then we compare those groups. And here's the key thing. In order for me to confidently say that catnip is effective as DEET, if I throw in a predictor, one of these categorical predictors in the model, and it indicates that there's no difference amongst these groups, and you'll see, we're going to go through a bunch of examples. Then I could say, oh, wow, catnip is truly as effective as DEET under many situations. That's quite the generalizable statement. And that's one of often the key approaches to meta-analysis is to make generalizations, right? You're overlooking details to reach a consensus. But sometimes those details matter. Sometimes they make a difference. And that's what we're going to do today, is we're going to check to see if studies, different species are consistent in their responses, if catnip oil versus specific compounds are consistent in their responses, if different experimental designs are consistent in their responses, and if we have consistency across all these different dimensions that impact the variability associated with catnip, then we could walk away saying, you know what, overall, catnip is as effective as DEET. But I'm not ready I'm not totally convinced that that's the case yet. I guess that's where I was going with that. And so, and so we need to start exploring sources of variability and whether they actually contribute to repellency effect differences in our overall effect. Ah, boy. Okay. So, last lecture, right? We took the grand mean, a random effect meta-analysis, a proper meta-analysis, and we found that essentially we got a null result. That there was no difference between catnip and DEET in terms of repellency effects, which was a neat finding, right? Now the social media, we already kind of dismissed a social media claim that catnip is 10 times more effective than DEET. That doesn't seem to be the case, but then now we have this other thing that we need to think about, is whether or not catnip is similar to DEET. And so my setup here again, I got R already set up, and we're going to begin our categorical meta-analyses. Without going into too much detail, this is a type of, again, a linear model, and so we could throw in predictors. Now, there's some mixed language in what we should describe these predictors, these things that could potentially impact differently the efficacy of a catnip. Some people call them moderators. Some people call them fixed effect. Those are all true. They are just kind of centered on different viewpoints in what type of modeling that you're doing. And so, for example, if you just see meta-analysis as an elaborate linear model, then you're going to call these predictors as fixed effects. But meta-analysts like to call these things moderators, just as a way to distinguish it from a regular fixed effect. And here's why I think so. It's because we're analyzing effect sizes. Effect sizes are already a contrast between something. And so now when you further parse those contrasts, you're kind of doing like an interaction effect analyses, where you have your main effects and you have an interaction effects. And so, for example, we're comparing catnip versus DEET, and now we're adding additional groupings to that. So catnip versus DEET for mosquitoes A, catnip versus DEET versus mosquito B, right? And so when you throw in a predictor or a moderator in your variable, basically you're looking at this, right? You're looking at an interaction test. And so maybe that's why we call them moderators rather than predictors or simple fixed effects in the jargon of meta-analysis, because they are meaning something different, because we are analyzing effect sizes. We're not just analyzing regular old-fashioned data. That's the That's the challenge with synthesizing study outcomes, is the outcome, the data, the raw data used in the meta-analysis is fairly complicated. Effect sizes are bizarre things. And so my setup here is I got R. I got some stuff already scripted. I think that's what you see right here. And basically, I'm just going to throw in different predictors in the model and see how things wash out. So for example, the first thing I wanted to test was, this is a totally just a super boring methodological potential moderator, is, if you remember way back in the lectures, the goal was to extract Hedges D effect sizes. These effect sizes use means, standard deviations, and sample sizes to compute an effect size. So for example, you have the mean response of catnip, and then you got the mean response with DEET. Use that to calculate an effect. But other studies report something different. They report counts. So the number of mosquitoes landing on a hand treated with catnip, and the number of mosquitoes landing on a hand treated with DEET. That's a count. You can't quite compute a Hedges D effect size with that stuff. And so I had to use an odds ratio. An odds ratio is just a way to calculate an effect based on counts. And then because they all share the same linear model, you could convert the odds ratios into a Hedges D. And so as a sensitivity analysis, right now I'm going to test whether or not the studies that reported things via odds ratios differ from studies reporting Hedges D. And this is just like a internal check for consistency to make sure that I'm not introducing any bias in my analyses by doing this conversion. That's a necessary evil in meta-analysis, is you will often have to convert things. And so the next stage when you do that kind of stuff is you need to double check, validate that decision on whether or not it's okay to pull together, to homogenize effect sizes that are kind of come from different effect sizes. So the moderator here, the model, I'm just going to quickly describe the model again. So we have a classic random effects meta-analyses using the DL approach to estimate the between study variance. The data set differs a little bit from the one I did in a previous lecture. This time I actually changed a sign in a few of the studies. I didn't do that last time and I regret it, but fortunately it didn't really change the outcome of the synthesis. Was I really just forgot to change the sign in some of the effects, and it's not really that many that have a sign change. I think out of the 120, there's like 6 that needed their sign changed. And so that's what this line does, is it converts some positive effects into negative ones and converts some negative ones into a positive one, because the response measure was the complement to the one I'm looking for. So rather than, I'm just going nuts here, rather than reporting things in terms of, say, for example, repellency, they reported things in terms of like not repelled, right? So the opposite of repellency. And so I need to invert the sign to make everything a common currency across effects. Okay. So the what you're going to see is the analyses are going to report the grand mean, just like a grand mean meta-analysis like we did in the last lecture, which is the just a straight up weighted average across all effects while accounting for the between study variability. And then below that, you're going to see that those effect sizes being parsed or grouped under different categories, with the goal to determine whether or not, by splitting the data into these different categories, to make an assessment of whether or not they differ, these groupings differ. If these groupings differ, okay, that means that that original the grand mean is not, I wouldn't say totally inappropriate, but it means that we need to be very cautious in making interpretations with the grand mean, because the data included in the grand mean are technically not homogeneous, right? Which violates one of the assumptions of making a synthesis level aggregation across effects. And so best case scenario, right, which would make it awesome for me to end the class really quickly, I wouldn't have to record many lectures, is that all the moderators I test today, if they all show no effects, then that final grand mean that catnip is as effective as DEET is true. That's we could conclude with confidence that that might be a true effect. Right now we can't do that. So first one that I'm going to test is whether or not the odds ratio based effect sizes differ from the Hedges D effect sizes. Like, I converted the odds ratios into Hedges D, but now I got to double check to make sure that was appropriate to do in the first place. And so here I throw in the category called source. I think that's all I called it. Nothing to... So the moderator here is called source, and I got this little thing that let's call it effects due to conversions. Okay, so this is my first one. This is a totally methodological test. I mean, everything stops if this says no. Right, if we conclude yes, there's a different, then that's a real bummer, because it means that my original conversions either were wrong, or that we can't, we got to drop all the studies that were synthesized with odds ratios. Hopefully this works. And then something funny happened here. What do you see? You do see this nonsense that I see. Okay, well, I gotta try something different here. Source, effects due to conversions. Let me try it again. Okay, well, something's messed up here, unfortunately, which is a real bummer. But I'll move on. This was supposed to show a really nice visualization, but really, it doesn't. Nonetheless, whew, okay, there's some funny business going on here. Oh no, that's not good. Okay, so I have 93 effect sizes that were based on Hedges D, which is the original effect sizes that I wanted to extract from the studies, and 35 were based on log odds ratios. And there's a lot of mumbo jumbo here, but the idea is to test whether or not the log odds ratio effect size is different from Hedges D, and the answer is no, but not really at a level that I'm totally confident with. Okay, so it is, they do not significantly differ from one another, but between you and me, there is something funny going on. The log odds ratios tend to be more on the negative side, whereas the Hedges D tend to be more on the positive side. Now, this is really complicated to tease apart, because these are probably derived from different studies, looking at different mosquito species, looking at other factors. This is really the reason why we need to do like a multi-factor analysis. I'm not going to do that today. Everything's going to be univariate, single factor analyses. Next class, I'm going to do the multivariate stuff. And then we'll be able to get to this problem. So the first one, just as a first pass, based on the p-value, which is not the best way to make a judgment calls, but I got to move on with the class. This will certainly be something that I put on the my wall of shame, is using p-values to make decisions on whether or not to include, exclude effect groups. Okay, so source for now is not providing evidence that there's a difference between those groups, which means that at face value here, me pooling hedges D effects and log odds ratio derived effects is okay. But man, it's not a strong test at all. Okay. Next one I wanted to test was oh, that's why I was messed up. I'm messing up with I'm playing around with the main model. Never mind. Okay, so things will get better at this point forward. Okay, next thing I want to test is another experimental design thing of all of the various ways in which research has been done to test repellency effects. I mean, this was really the most inconsistent thing across all studies, is everyone's kind of using their different approach to test whether or not catnip repels. What I think the best way to do it is to do an arm and cage trial, where you have a real human, you put catnip on the arm, you put DEET on the other arm, you stick your arms in the cages, and then you evaluate the repellency effects. I got a message on my phone here. Okay, sorry. So where was I? Ooh, total distraction here. And so I'm going to look at different experimental designs to see whether or not they're consistent, right? Testing the consistency, whether or not they're providing similar effects. And I think the moderator variable that I called it here was called experiment type. Effects due to design. All right, let's see what kind of weird stuff comes out of this. Okay. All right, so oh no. Okay, so there we go. We what this mean? Okay, so here we have the list of all the different types of experiments that were done. Okay, so we have arm and cage trials, which is the bottom. 56 effect sizes were based on arm and cage trials. A bunch of studies were based on these choice chamber experiments. It's either like a Y tube, where you have like mosquitoes and they make a decision on where to fly based on whether or not the repellent is pumped. Many variations on that design. We got field trials, where you have people sitting in a field and then people counting the landings on the mosquitoes. We have substrate in cage trials. These are anything that does not use a human inside the cage, right? So humans, you're sticking your arm in, but sometimes you use like a substrate, a piece of filter paper with a little bit of catnip oil on it, or some netting with some catnip oil on it. Sometimes you heat it up, or you pump a little bit of CO2, or you bait it with like a CO2 trap. There's like a whole bunch of different design things. And then finally, the last one was a well assay test, which are little cups with simulated blood. And then you throw in one mosquito or a few mosquitoes, and you measure the amount of time it takes for them to get excited about the blood. And there's the test here, we rely on a QB test, which is like a type of heterogeneity test that evaluates differences between groups. It's an omnibus test, so if any one of these pairwise comparisons between the groups differ, right, And potentially we could have many differences. 1, 2, 3, 4. We got 5 groups, 5 by 5 potential contrasts amongst the groups. If any one of those differ, the omnibus test will flag it off saying there's a difference occurring here. And it's saying that there is a difference. Just eyeballing it here, I could say it's probably the substrate in cage differs significantly from the arm in cage. To me, the arm in cage trials are the ones that provide the best evidence. I mean, you got a human. You got a human in the experiment with mosquitoes. The field trials, of course, are better because it's like way more, it's applied in practice. You have a diversity of mosquitoes, species, diversity of mosquito ages, whether they fed or not, whether or not they've already laid a clutch of eggs, right? You get that whole variability tested all at once. And so, unfortunately, already, I could say, you know what? Catnip is not always as effective as DEET. Because it seems like if you have humans involved, then this kind of breaks down. And so there you go. So I need to think more deeply what this means biologically, that, you know, experimental design is impacting the impact of the outcome, but that's a failure right there. Experiment type failed. So that aggregation that we did in the last lecture, that we found that catnip is as effective as DEET. Now we can't say that with confidence at all, because we know that experimental design significantly impacts that effect, which means that it's not appropriate for me to do that original analysis because I'm aggregating things that actually differ. Substrate in cage trials differ from arm in cage trials, right? So if you're using a human and not some sort of simulated human thing, you're going to get different results. In fact, almost like competing results. You're going to find that catnip is better than DEET if you don't include a human, but if you include a human, then you might find that DEET is more effective than catnip. This is the type of heterogeneity that causes a lot of headaches. I mean, when it comes for me to pull together the manuscript, this is going to be super tough for me to explain. But for the sake of moving on with today, I got 3 more things I want to test. I want to test the variability across mosquito species, and then finally the variability associated with the repellent itself, whether essential oils or derived compounds are differ in their impacts on mosquitoes. We already know experimental design impacts the efficacy of catnip. All right, let's compare across mosquito species. Effects due to different mosquitoes. Okay. All right, again, significant difference in the QB test, which is our omnibus test of whether or not things differ. We have many different types of mosquito species included in a data set. All the usual suspects. We got all the really important groups, the Culex, the Anopheles, and the Aedes. These are some of the true bad guys in terms of vectoring diseases in the world. We got the mosquitoes that vector malaria, vector Zika, dengue, West Nile. All the baddies are here, but their responses to catnip is just all over the place. I mean, it's inconsistent amongst the Culex mosquitoes. It's inconsistent among the Anopheles mosquitoes, and it's inconsistent amongst the Aedes mosquitoes, the 3 groups. I mean, yeah, there we go. So like this to me indicates that catnip is not an awesome repellent because it's inconsistent in how how it works with different mosquitoes. Maybe there's like a phylogenetic effect here for you guys. That might be jargon here, but it means that, you know, mosquitoes that have a related evolutionary history might respond similarly. But this showing that no, that's probably not happening. You have a semi-closely related mosquitoes, and they're acting super weird all over the place. With the caveat, though, that this variability might be associated with the experimental type, right? We already found that studies differ in catnip efficacy based on experimental design. Now we found it that mosquitoes also differ based on experimental design. The two may not be independent from one another, right? Some of these species are tested one way, other species are tested a different way. This is like how things are knitted together, which is why we need to do the full multi-factor analysis to include all this stuff in and then see what washes out. But right now we're doing univariate tests. We're looking at things separately. But the conclusion is the same. That original average across all those effects that I did in the last lecture, not allowed to do that. Slap myself in the hand. I do not have a homogeneous data set. There's different effects across studies that I should not homogenize, I should not average across. Okay, last one, or last two, is the repellent type. I got two here, so they are similarly repellent type effects due to the repellent due to like people are testing catnip, the original species, the Nepeta catarina. I don't remember what it is, but some are testing a different species of catnip. Some people are testing catnip oil. Others are testing catnip oil plus carriers, different types of compounds. Other studies are testing the derived compounds from catnip oils, right? The active ingredients, the nepeta-lactones, or variations of that. And so this is what this analysis now is going to test to see whether or not that is the case. Let's see what washes out. Oh, still got different species here. So repellent type is not, did I spell that right? Did I have two? Yeah, I misspelled it. Okay, here goes. Let's plot it. All right, whoa, there we go. Huge variability again amongst the different types of repellents. So we got the Nepeta catarrhea, which is the conventional catnip plant species. We got the Nepeta parnasica, which is another species that was tested. The two show totally different effects. To me, that indicates, okay, so maybe not all species are alike in terms of the active compounds in the plant. And then you have the contrast between the two types of isomers of the nepeta-lactone. Isomers, it's chemicals could have handedness. Okay, so they're both structured the same way, but they just have like a right hand and a left hand to it. They're symmetric. And nepeta-lactone, the active compound in catnip, comes in two forms like that. And there's whispers in the literature that these forms actually differ in their efficacy against mosquitoes. And looking at the data set, doesn't look like there's quite the difference between the two. Although I gotta be honest with you, a lot of studies already concluded that there was a difference. And so what they tend to do is just like remove one of them and only test one of the compounds. Other studies I try to get a, because plants differ in the ratio of these two isomers, these two variations of the same compound. Right, so there's a lot of this one, but little of this one in the plant. And so I think there were some studies that try to balance the two, and that's what the racemic napatolactone, someone tried to balance the quantity of the two chemicals in the test. That study concluded that there was no difference between DEET. And then studies just using regular catnip. Now, here is described as catnip because in the actual paper, they didn't describe the species. They were like, we got catnip oil, but there's no indication of like what species. Like we could assume that it's the Napatolacta catarrhea, but I'm not confident in making that call on that, so I just leave it as is. And then finally, the goofy one, the 4AS, 7S, 7AR napatolactone. That's just another way to describe. It's a synonym for napatolactone, with a more chemically informative synonym for napatolactone. So another failure. We got another failure here. This one's a big one where whether you test essential oils or whether you test the compounds, you get variability in catnip efficacy against mosquitoes. So we failed. We failed out of the 5 so far. We failed on 3. We almost failed on the first one, which was the comparison between the Hedges D and the odds ratio. This is not looking good for catnip. This is massive, massive inconsistency in repellency against mosquitoes. Okay, one last one. Last one is to like simplify this. So a big chunk of meta-analysis is to like create these groups, but this group is like diverse, and there's some of these things you could group together, like the isolated compounds you could group together. You could group together the essential oils ones, you could group together. And so that's what I'm going to do here, is just group together a lot of these things. Like even though there's 2 different, napatolactone is an isomer and it has 2 different variants, I'm just going to group those together. I think I call that repellent class. Next to the all right, let's run the analysis, see what washes out, and we'll be done for today with a rather disappointing interpretation of last lecture's outcomes. Okay, so by grouping these things into similar categories, the QB test concludes that there's no difference between these classes of groups. So if you compare essential oils versus the compound, they show similar effects. But unfortunately, I know that this is an inappropriate thing to do, this subgrouping, because we found in the other analysis, the one that I just did, that the individuality of the compounds actually does have an impact. So I can't simplify my data set, because these small groupings actually do have important effects in predicting the efficacy of catnip. All right. Well, I'm just going to leave it at that. Whoops. I'm just going to leave it at that. Okay. Well, previous lecture, walked away totally shocked, thinking that catnip performed just as well as DEET. But now I know, catnip is inconsistent. Inconsistent both in the outcomes of different trials, inconsistent in terms of how mosquitoes respond to catnip, inconsistent in terms of the actual exposure of catnip, whether it's an essential oil or derived compounds. Inconsistent in some of my methodological practices of like me converting things into odds ratio. This is like a triplet, quite 1, 2, 3, 4. I don't know what the 5 word is. This is a huge bummer. But that's the point of meta-analysis, right? If I would have stopped the project last lecture, I would have totally misled the entire literature. Everyone would have been like, holy smokes, catnip is the best thing. It's just as good as DEET. Let's use it. But today we find out that, it's inconsistent. It's one inconsistent thing. And some of the inconsistency is due to the variation associated with experimental design. The experiments are inconsistent, which results in inconsistent outcomes. Layered on top of that, there's inconsistencies across mosquitoes and the chemicals. Whew. Next lecture, I'm going to throw in a bunch of continuous predictors. So not things that group things in categories, but try to do a meta-regression style. So for example, we'll compare whether or not there's dosage effects. So rather than categories, we got a numbers comparing across effect sizes. A dosage, we're going to look at, what else was a numerical here? I can't remember right now. And then a lecture after that, we're going to do the proper way, which is like a full factor analysis. We're not going to do these univariate separate tests. We're going to include all these factors into one model. We could see how they interact, how they impact each other, maybe even assess what's important and what's not important. All right. Let's keep pushing forward. Take it easy.